Hi class. Let's continue to work on energy. So let me bring your attention to something we've done before. So this is the floor, and here you have a mass m. And so here we're just going to let this mass go from rest and let it fall down. So you know that eventually, a time later, this mass will fall right here, and we can say that U has fallen a height h. So this could be anything, right? So mass could be 10 kilograms, height would be 1 meter. It just fell. Uh, and what I want to do is I want to ask you to write down what the work that the force of gravity had to do in this object, right? So as you know, here, because it has mass, there needs to be a force of gravity that pulls this down. And he has fallen a distance. He has fallen a distance of h. So if you remember, the work equation equals to force times the distance. And if you remember what these arrows mean, it's you have to multiply this by the cosine of the angle that F and D makes. Now D is just a vector that points down like this. So there really is, there is just Fg times D, right? So there's no modification that needs. Basically, what it comes down to is Fg times D is the length of D is height times the height. Basically, if you want to know the full version of this is cosine of 0 degrees because they point in the same direction. But cosine of 0 degrees is just 1, right? In force of G, you know what that is, so we end up saying, look, the work for here is mass times gravity times height, okay? So if you have a block and you just drop it, work, and if you want to look at the free fall in terms of the force of gravity doing work on the object, then that work turns out to be mass times gravity times the height that the object drops. Okay. So now I'm going to ask you to do something, to try to figure something slightly different here. So instead of just a flat surface, suppose we have mass m. And that mass m is now going down an incline. And what we know about this incline is that the difference in between this point and this point, we're going to call that d. So that's the distance. So from here to here, the distance is d. And let's say that we already know ahead of time the height. So, if you take this here, from here to here, we know that this is height, right? Now the third, you can imagine you can make a triangle out of this. So for completeness sake, this is, I'll call this x. So there's a triangle here. So the ramp itself is d. That's the length of the ramp right here. The height is h. And then this side, this angle here is x. Now, if you remember from when we did inclined planes, there's still a force of gravity pulling this mass down. And if there's no friction here, this is just going to slide down the ramp. What I'm going to ask you to try to do on your own, if you'd like to try, is figure out what the work here is. What is the work done by the force of gravity to pull this mass down this ramp? All right, so let's try. I'm just going to go ahead and do it. So this again is force times distance. And now this turns out to be force of gravity times distance times the cosine of the angle. Now we gotta find what this angle is. This angle here is the angle in between the force of gravity and basically the direction in which the ramp goes down. Because remember, the displacement vector goes from here to here. So that's the direction of displacement vector, right? And the angle goes down, and force of gravity goes down perfectly like that. And I hope that you can see that this angle here, theta, is the same angle here. Basically, the angle in between, and let me write this triangle here. So what I'm saying here is I'm going to write two triangles here. If you take the angle in between force of gravity and the displacement vector here, if you take this angle right there, which is that angle in light blue, is the same angle as this triangle here. So we also have this other triangle that is height x and the amount of displacement d, or the distance, right? And this angle theta here is the same as that angle right there. Actually, let's do this. So this angle theta there is the same way as this angle theta there. Why am I going through the trouble of showing you that this angle here is the same as this angle? Because look at d cosine theta. When you look at this angle here, d cosine theta, that's equal to h, right? So you can imagine this, if you had just d and you wanted to decompose and find what h is, you gotta use the cosine of the angle. So that's what this is. So for this case, this whole thing turns out to be just h, right? Let's see, hold on. Let me erase that real quick. There you go. So let's go ahead and just open this up then. Then the work done over here comes down to mass times gravity times height. This work here done by an inclined plane, or the work done by the force of gravity pulling something down an inclined plane, is the same as the work that gravity did for the same mass just falling off. This tells you something very important about the work that the force of gravity can do on objects. It does not depend. It does not depend on the trajectory of the object. It only depends on the height. It only depends on how much, basically how much it falls. And by what I mean is that if I had, let's say I had a path of marbles or something. I don't know. It could be anything. First marble falls down 1. Second marble falls down here 2. Third marble goes all the way here and does something weird, and then 3. And then some even stranger one goes like this and like that. 4. The work done by if their masses are the same, then the work by gravity on object 1 equals to the work on gravity by 2 equals to work um, from work of the force of gravity on 3, and the same with 4. It only depends on the difference in height of the initial and the final. So if they all drop the same height, then all their works are the same. Okay. Now this is what we call a conservative force. A conservative force does work in a way that only depends on the position. Now this is just I don't expect you to fully understand that definition, but what I want to tell you is this: if a force is conservative, as in its work only depends on some form of position, this work becomes something very special. It becomes potential energy. And so in this class, the first potential energy term you're going to see is the gravitational potential energy, which is the same as the work done by the gravitational force. So gravitational potential energy here equals to mass times gravity times height. And there it is. So I'm going to solve a simple conservation of conservation of energy now, using gravitational potential energy and kinetic energy. And I will use your activity. So the last activity you guys all did as a lab had you look at things rolling down incline planes. So you had an incline plane like this, and then it stopped, right? It was, I think it was some sort of car, if I remember correctly. So some sort of car, and then what happens here is you know the height in which you're dropping this car. You know that this distance here is height. So from here to here is h. And then right down here, you had something called velocity final, right? And then at some point, friction starts taking over. So before this green line here, there was no friction. And then all of a sudden, in this area, there is a frictional force that points this way, force of friction. Okay? Good. So force of friction. And you were asked about the relationship in between the final velocity down here, as you change the height, right? And the way you did in the activity, you just kept changing the height and you kept seeing how this changed. So let's go ahead and see why you got what you got, right? So this is a conservation of energy. So the simplest form of conservation of energy is that energy initial equals to energy final. Now, with every energy conservation problem, the next thing you ask yourself is how many types of energy are there? So here, there's no motion, but there is gravitational potential energy because this thing is going to drop a certain height. And here, the thing will start, it will be moving, therefore you have kinetic energy. So let's go ahead and say There's kinetic and gravitational potential energy. So initially, that's kinetic energy initial plus gravitational potential energy initial equals to kinetic energy final plus gravitational potential energy final. And if we open this up with the expressions we know for what these are, this means that this is 1/2 mass the initial speed squared plus and now the initial here means that you're all the way up there, right? So initially you have all the gravitational potential energy, and then as you drop, it goes to 0. So this is mg, and the height equals to 1/2 mass velocity final squared plus now what happens here is that this goes to 0. I'm not even going to write this down. So this one here goes to 0 because you already hit the ground. So plus 0. Okay. Now, in your simulation, the car was not moving at the beginning either. So this also goes to 0. And if you notice, mass is gone. And now the only things that are left is gravity, which is a constant, times the height to drop this car equals to 1/2 velocity final squared, which means that the velocity in which the car hits this part of the track right there is proportional to the square root of height. And I think one of the questions was, what happens if you double the height? And it basically is velocity increases by less than double a factor. That basically, what they're trying to tell you is that if you double this height, you're going to have a square root of 2 increase, which is 1.41. So I know the wording on that activity may have been a little curious, but this is where it comes from. It comes from the fact that once you do energy conservation, you find that height and the square of the final velocity end up being related. Okay. Now the last thing is there was a frictional force here, and now he asks you about the stopping distance, right? I think he asked you about the relationship in between the height and this stopping distance d. Now, if you think about it, the displacement vector is going to be pointing to the right, and force of friction is going to point to the left. So you can imagine that to stop this car, the work needs to be equal to the speed coming in, which is the total kinetic energy final, and it has to be minus force of friction times the stopping distance. So let me take this idea and write this down over here. So if we take that, the idea work needs to be, to stop the car, you need to have the work do kinetic energy final equals to minus F force of friction times the distance, which is the stopping distance in this case. Actually, the work needs to be the negative of it because you have to bring the kinetic energy back to 0. But what we do know is that the kinetic energy, if you look at this equation here, kinetic energy here is 0. Gravitational potential energy final is also 0. You find that kinetic energy final is really just gravitational potential energy initial. So I can go ahead and just say, look, this has to be really the gravitational potential energy initial. So when you write this all out, you will find that the force of friction times the stopping distance has to be equals to mass times gravity times height. Gravity is a constant, mass is a constant. The force of friction here is a constant. So it basically says from that activity that the distance is proportional, the stopping distance is directly proportional to height, which means that if you increase the height in which the car drops, the um, the the stopping distance will increase in the same way. So if you double the height in which you drop the car in that ramp, the stopping distance is also going to double. Okay, so I hopefully this was a good thing to use for you to get a grasp on gravitational potential energy, and also how to navigate the wording that they used for the lab activity that you did last time. All right, have a good day, and I'll talk to you all soon.